Great to be here today, talk to you about GenAI and HeatWave. To introduce myself, I am Milos. I have a PhD from MySQL in Switzerland. And then in 2018, I joined Oracle at our office in Zurich. And I've been working at Oracle Labs on some machine learning projects. And a year ago, I joined the MySQL HeatWave team, and I'm working on generative AI. And this is what I'll be talking about. I will take a huge risk and introduce how generative AI works in a nutshell, hoping that maybe not everybody really knows everything. And then I will talk about our GenAI ecosystem in HeatWave. I will present some challenges that we had in developing this and show you a few examples of applications that were built with HeatWave GenAI. So when we talk about generative AI and large language models, then we should know that they are built on top of transformers, which is a type of a neural network architecture, which is designed for handling sequential data, such as text. And these models are usually very large models. They're ranging from several billion to several hundreds billion parameters. And they have been trained on many, many data, like billions of data samples. And what they are really good at is predicting the next word or the next token that comes in a sequence. So here we have this example in which the user is inquiring what to do in Brussels, and a little bit of instructions for the LLM. And then in red is what the LLM could be generating as a response. And at this point, the LLM would generate, so at every step, the LLM would generate a probability distribution over its entire output vocabulary. Let's just imagine those are all the words that you have in your dictionary, and would then sample from this prediction, and with high probability, the next word that would appear here in this sequence would be Brussels in this case. But how does Transformer do this, and how does Transformer capture these relationships between the sentences or sequences in the words? And the answer lies in the embeddings. Embeddings are at the heart of Transformers, and they are dense vector representations that capture semantic meanings. So if you have some words like Nobel Prize or Max Planck, basically they are converted into vectors, so a sequence of numbers. And this is what the neural network has to work with. But these words, these vectors have also semantic meaning embedded into them. So then they are refined as they're passing through the transformer. They are passing through the multiple layers of attention and feed-forward network, and they're refined. And by feeding many, many examples to the network is learning to extract rich contextual information from them. So basically, we have a lot of dimensions, let's say thousands of dimensions in these embeddings, and the transformer is arranging different words in different dimensions, and it's kind of trying to group them according to some properties in various dimensions. And I cannot show this in like 1,000 dimensions, but if it's plotted like in 2 dimensions, you can see kind of that some terms that are close to each other, for example, years around the turn of a century, would end up close in the same part of the vector space, and some unrelated terms would end up far away. So basically, LLMs are not only useful to predict the next word, but also to generate those vector embeddings I was showing. And they can be embeddings of the word, but they can be embeddings of the entire sequence, sentence, or paragraph. And vector store is a specialized storage system for high-dimensional vector embeddings. And the idea is to take some documents, parse them, segment text into smaller chunks, and then embed. And for each segment, you would end up with one multi-dimensional vector, and then all these vectors would be stored into a vector database. And by doing so, you would allow users to perform similarity search in the contextual space. So unlike just the keyword search where you're looking for a car, here if you have a document which has vehicles but does not mention the keyword car at all, you would still be able to find it using semantic search. And now let's take a look how vector store can help LLMs. So LLMs are really good at processing information, predicting the next word in the sequence, but they lack the ability to interact with the outside world. So they're trained on public internet, books, Wikipedia, so a bunch of public data, but what they don't know about is your private data and your enterprise data. And basically, there is the goal of the concept called retrieval augmented generation, or RAG in short, is to empower LLMs to interact with external data. So you would take some private or enterprise data, embed it, store it into vector store, and then you would be able to perform similarity search using those embeddings. Here is a concrete example. If you were just using an LLM without RAG, and you were asking about heat wave, the answer would most probably be about the weather phenomena, because the LLM does not have the domain-specific knowledge. But if you're now using LLM with RAG and you have preloaded some documentation about heat wave, then the answer would probably be about MySQL heat wave. Okay, now with these basics, let's look at the GenAI ecosystem HeatWave. And HeatWave is a single system, as Jari was already talking about, that offers transaction processing, analytics, machine learning, lakehouse. And since the 9.0 release, it also offers vector store, scale-out vector processing, and LLMs. And it allows a user to ask questions in natural language and get back the answers, and those answers can contain information about source from the documents that the user is storing in object store. When we speak about LLMs, in HeatWave we offer multiple choices. The first class is what we call in HeatWave LLMs. Those are executing on our HeatWave cluster, which means that data does not need to leave HeatWave at all. There are no external API calls being made. Those are models such as Llama 3 with 8 billion parameters or Mistral with 7 billion parameters. And those are not the largest models out there. They are smaller models, right? And they offer solid quality, but they also give you a good price performance space. And then we tightly integrate with the LLMs offered by the OCI generative AI service. They're offering larger models such as Cohere Command or Llama 3.1 70 billion, so a degree of magnitude larger model. And those have excellent output quality, but they also come at a higher cost. They are running GPUs and you have to pay them in addition. Charlie already mentioned that we have a new data type in MySQL and HeatWave, which is a vector. And thanks to this vector type, we can store vector embeddings. And here, just imagine that we are creating a Wikipedia table and you want to store content from various pages in Wikipedia. So you have all the text data here in this column, and then you have the embedding, which is, in this case, vector with 1024 dimensions, which contains the entire context of that page compressed into 1024 numbers. And then, thanks to the distance function, you can perform similarity search, and you can find what are the pages in Wikipedia which are closest to your query. If you're looking for cars, you may find pages that are talking about vehicles as well, as I was saying. Creating a vector store means that you would run a pipeline like this. It's a complex one and it has a lot of steps. It starts by first you need to discover what are the documents that the user has. You need to parse them. You need to take that text and chunk them into segments. You need to embed the segments. You need to create a table. You need to design the structure of the vector store table. You need to insert all the data, metadata. And when you want to use it, when the user asks a question and you want to use it with RAG, you need to ensure that there is a consistency between the embedding model that has been used at the vector store creation time and at the lookup time. Then you have to select from all the vector store tables the correct one. You have to perform the similarity search with the correct distance function. You have to choose which LLM you want to use, pass the fetched information as context, and generate the response. And all of that in HeatWave is done in a distributed fashion across the nodes in our HeatWave cluster. So each step stage, we read files from object storage in parallel. We segment them in parallel. And then we also pass them through the encoding models in parallel. And finally, we write back the result into object storage also in parallel as a vector store table. And luckily, we offer also a high-level API. So instead of having to run all those 15, 20 steps that I have showed, you can just point us to your data, let's say a prefix in an object storage bucket, and we will automatically parse, ingest, and encode this data and store it into a vector store table. And then you can just fire up another client and you can start asking questions, calling a different API, which is another swap procedure for RAG. And there is really no complex glue logic or no really AI expertise needed to be able to start using this. So in summary, generative AI in HeatWave combines LLMs, lakehouse ingest, and vector store. It all starts by you loading some documents into vector store. They are then read in a distributed fashion from object storage. They are parsed, embedded, and stored into the vector store table. And then when you have query coming in a natural language, you would embed this query. You would perform similarity search. You would generate the prompt, which is being passed to the LLM, and you would then pass the result in natural language back to the user. Another differentiator that we have in HeatWave is a synergy of generative AI and AutoML. So this allows you to take advantage of traditional machine learning models we have in HeatWave, such as classification, regression, recommendation models, and to use natural language to interact with data and with their outputs. Also allows you to reduce the search space. So you get more accurate results because you can filter out irrelevant data. You don't have to pass all the data to the LLM, and also you speed up the inference because LLM inference is expensive. So if you would like to pass all the data to the LLM, it will take forever. Right. So now I would like to mention two challenges. The first one is, how do we run LLM inference in a database? We know that LLMs are large models and they are very resource hungry. But the key observation is that they don't really need to use the entire range of a 32-bit float in order to perform well. So it turns out that it is possible to quantize them and to store the model weights in a lower precision data type, such as an 8-bit integer or even like a 4-bit integer. And by doing so, there is obviously some information loss. It's kind of a lossy compression, but models get to maintain an acceptable level of accuracy. And also with quantization, then we get like a smaller model size. Here are some examples of how much roughly would a model with 8 billion parameters, such as Llama 3, take on disk in different representations. And smaller models have basically smaller requirements of memory bandwidth. And after all, they allow us to run inference in HeatWave on CPUs. We don't have GPUs in our HeatWave cluster. And it allows us to fit the model in the allocated memory budget that we have. Another challenge is that RAG requires that precise and complete segments are retrieved from vector store. And as we are doing segmentation, it can often happen that cohesive context is split into different chunks or different segments. And here is an example that we have some document that is talking about database indexes. And once that is ingested into a vector store table, it ends up across multiple segments. And now a user comes with a question, how does indexing improve database performance and what are the trade-offs of using indexes? And now the key challenge is, what is the value of the n citations parameter? Or in other words, how many relevant segments do you want to retrieve from vector store? They are obviously, for each of them, you have like some kind of a distance function that you can compute. But how many of them do you want to select? And if you choose 3, you will include the first 3 segments, and they have the information about benefits, but you will leave out some information about trade-offs. And the LLM will not get the complete context, and the answer will not be perfect. And for that, we have added some additional retrieval options. Maximum distance, segment overlap, and percentage distance. And in general, they give users more flexibility and control over context retrieval. So on the same example, this now allows you to increase this n citations parameter, but dynamically retrieve segments with distances, in this case, up to 20% higher from the nearest segment. Nearest segment is 0.35. So if this was some histogram of distances of different segments that you have in vector store from the query, you would end up taking dynamically 20% higher than this, but the irrelevant one would be left out. Okay, and we arrived to some example applications. The first application is an example of the synergy between the AutoML and generative AI in HeatWave that I was talking about. So here we have this application which is continuously ingesting some unstructured logs and is running unsupervised anomaly detection algorithm, which is offered in AutoML in HeatWave. And what this does is it trains a model, it tries to learn the distribution of normal data that you have in your logs, and it produces a report like this. And you have here a timeline, and you have an anomaly score. And let's say that here is a report. This is like a sequence of logs that have a high anomaly score. What you can do now with this synergy with the GenAI is you can pass that sequence of anomalous logs to an LLM and ask it to summarize it for you. So you can produce an incident report, which is in natural language, which is easier for an operator to consume and understand. And here is how it could look. This would be the example of the sequence of logs. So sure, yes, you can return that, but you can also simply say, hey, can you summarize the main problem in the sequence of logs? And then you will get the response in natural text. Okay, the second example is the MySQL shell extension for Visual Studio Code. Scott was talking about MySQL shell, and this is the extension with the GUI. This is readily available. You can install it in the Visual Studio Code and use it. And it has 2 components. The first one is the HeatWave Lakehouse Navigator, and the second one is HeatWave Chat. So what Lakehouse Navigator allows you to do is to browse objects in your object storage bucket, select the object that you want to load into a vector store table. And in this case, we are selecting some HTML files. So they are saved from several web pages about Formula One and Oracle Red Bull Racing Team. And once we select them and we click the Start Loading Task button, basically that entire ingestion pipeline is launched in the background, and we are ingesting data in the vector store table. And we see that this one is in progress. There may be some other vector store tables that are already loaded, and you have a nice overview of that. And once your table is loaded, we have the second part, which is HeatWave Chat. It's a chatbot which relies on RAG, so allows you to ask questions, in this case about the Formula One championship, and it will source answers from the HTML files that you have loaded, and you are able to ask questions about the Red Bull team or about their collaboration with Oracle Cloud, how do they use ML, and so on. And at the same time, you will get, on the right-hand side, you will get the list of the vector store tables that has been discovered. You will get the list of documents that have been matched and the closest segments that have been used in generating the response. And the last example is an e-commerce platform. Here we have a web shop, which is backed up by a MySQL database. And you can take advantage of HeatWave GenAI if you want to collect feedback about different products. The user can write a review, and once it is approved, obviously, you can just insert it into a database. But at this point, it is very simple for you to also use GenAI to analyze the sentiment, to know if that feedback is a positive or a negative one. And you can do that, in this case, in this example, by writing a really simple JavaScript program that runs in HeatWave. Here, you take the review that has been submitted by the user and you pass it into a prompt, and you're really just giving the instruction to the LLM to describe the sentiment using a single positive or negative word. And you pass that prompt into the ML API and you get the response. And once you have that sentiment, you can go and update the record and you can store it in the database. And you can go one step further. You can write another program. Again, it can be a JavaScript program, or it can be like a SQL store procedure if you want. And this time you can extract all the positive reviews and all the negative reviews. And then you can pass them on to the LLM to produce summaries. And once you have the summaries, you can directly show them on the web page. This is all I have today. So yeah, thanks so much, and happy to answer questions.